These were the 3 linear algebra questions from Stephen on the exam. These were the 3 optional questions in his part. The first question on vector spaces and subspaces, linear transformations, and transformation matrices from one basis to another. Question 7 had a bit more on linear transformations, looking at their kernel and image. And a part B question on eigenvectors and eigenvalues. And then question 8 was surrounding issues surrounding inner products. Part A is applying the Cauchy-Schwarz inequality to get an upper bound on an integral, which doesn't have a closed form integral. Part B was proving this relationship amongst the norms of 2 vectors u and v. And then part C was applying the Gram-Schmidt orthogonalization procedure to get an orthogonal basis from a kind of average or typical basis. Okay, so let's start at the beginning. So we'll work through these, and please do stop me at any time if you've got any queries or anything you're unsure about, or you'd like me to clarify anything. So question 6a is about vector spaces and their subspaces. So the context here is we're dealing with P3R, which is the vector space of all polynomials of degree less than or equal to 3 with real coefficients. Okay, so this is a vector space. There are very natural operations of addition and scalar multiplication on these objects. You add 2 polynomials together by adding the corresponding coefficients. And you take a scalar multiple of a polynomial by multiplying each of the coefficients by whatever scalar you take the multiple with. And those 2 operations of addition of polynomials and scalar multiplication, they do indeed satisfy all the long list of axioms for how they interact with one another, and so on. So they are a vector space. In this question, you are given 2 subspaces, sorry, 2 subsets, W1 and W2, which are defined as 2 subsets. And the question is, do these subsets form a subspace on their own? Naively, if you're just working straight from the definition, to check that they form a subspace of the vector space would be quite a long task. You've got to check all the axioms and so on to check whether these subsets form vector spaces in their own right. But since we know they're coming from a vector space which is already established, most of the axioms for a vector space are going to be satisfied automatically for W1 and W2 because they hold inside P3R, and W1 and W2 are just subsets of P3R. So there's a theorem called the subspace theorem, which just gets rid of all it removes any reference to the axioms which are going to be automatically true, and just gives you the minimal condition that you have to check in order to prove that a subset is a vector subspace of the enclosing space. So this is it here, theorem 1.1. So this is going to be the one we're applying. V is the surrounding vector space. W is the candidate subspace. So W is a subset of V. And to prove it's a subspace, you've got to do, well, strictly speaking, 2 things. You have to be sure, you have to emphasize or justify why the set W is non-empty. So you should be able to point to an example of an element that it has. Then you just have to check that any linear combination that you can form like this, which is an alpha U plus V, where U and V are any 2 elements from W, and alpha is any scalar from the scalar field, which for us will be the real numbers, You have to be able to prove that this linear combination alpha u plus v will always be contained in W. It will never stray outside of the subset into some of the space in V, which is not in W. Okay? So this is, in English, what we're doing is we're proving that the subset W is closed under linear combinations. Take a linear combination of two vectors in W, you are still remain in W. If you can prove that this is always the case, then W is a subspace. Any questions on that result, or just on what the task is? So your solution is going to be one of two kinds. It's either going to be a proof that alpha u plus v is always in W, thereby proving that the subset is a subspace, or it's going to be an exhibition of a counterexample. You realizing that the subset is not a vector subspace, and to nail that, to prove that to the reader, you have to offer up a counterexample, which is a specific choice of alpha u and v, where the u and v are clearly in W, but the combination alpha u plus v is outside of W. If you can demonstrate, show that happening on one occasion, then it's not going to be a subspace, because that's a proof that it's not closed under linear combinations. So you're two types. You've either got a general proof that it's closed, or you've got a counterexample pointing out one instance where the closure is broken. Okay? So these are potentially a bit tricky because you don't know what kind of thing you have to provide, because you don't know whether it's going to be a subspace or not to begin with. Okay, so the notation is your typical polynomial is a0 plus a1x plus a2x squared plus a3x cubed. So in the first part, we've got this subset W1, which is the set of every p polynomial px, which is a0 plus a1x plus a2x squared plus a3x cubed. So these degree polynomials are four-dimensional objects. They require 4 parameters to specify them. And the condition for membership of W1 is that the sum of the absolute values is strictly less than 1. These AIs are real numbers. I mean, that it doesn't need to be said. That's automatically understood. So this is the condition. So it's certainly a subset. First of all, we should just check, is this non-empty? Is there any polynomial at all that's in there? Well, the polynomial, let's say a half x. That's certainly in W1. If you add up the absolute values of the coefficients of this polynomial, you just get a half. It's clearly strictly less than 1. So that polynomial is certainly in W1. So W1 is non-empty. Does it look like it's going to be a subspace? Hands up who think it will be a subspace. Hands up who thinks it won't. Okay, a lot of people saying it won't. So that's good intuition. It is not a subspace. The reason, well, there might be multiple reasons, but this condition where the sum of the absolute values of the coefficients has to be held less than 1, I mean, it's easy to, even if you're starting off with a polynomial that does satisfy this, yeah, so you have to think that way. Starting off with a polynomial that does satisfy this, can you form a linear combination out of that polynomial or polynomials which will break this condition? Well, yeah, this condition is saying something about the sizes of the coefficients. But by taking linear combinations, you can easily make the sizes of the coefficients huge. Just multiply them by a big scalar. That will make the coefficients very large. So surely you can arrange it so that this condition will then be broken. And we can certainly do that. So let's take this one polynomial and show it playing a role in a counterexample. So the condition does not look linear. As we can arbitrarily increase the coefficients by taking a suitable scalar multiple, forming a suitable scalar multiple. That's a nice description, a nice kind of lead into the counterexample, but to really nail it on the head. So here's our, e.g., take u to be this polynomial at half x. Take the scalar alpha, well, let's go to 10. Let's use the scalar 100. Of course, anything bigger than 2 will work. Just take 100. Alpha times u, and to strictly match it to the subspace theorem, let's just ignore the second vector. So alpha u plus b is just 100 times a half x. This gives you a polynomial 50x, which is certainly not in W1. As the sum of the coefficients is equal to 50, which is not strictly bigger than that. Okay. That's all you need to do to prove that that is not a subspace. It's a perfectly good subset. There's loads of polynomials that are in it. They all have pretty small coefficients, though. Never a coefficient bigger than 1, and always with the sum of the absolute values less than 1. So there's certainly an infinite number of polynomials in W1. There's plenty of polynomials there, but there's no subspace structure there using the same operations of vector addition and scalar multiplication. There's no subspace there because it doesn't contain lines, because when you take any vector that's in it, multiply it by a suitably large scalar, you'll move outside the subset. Okay? So W1 is not a subspace by the subspace theorem. Is that okay? Is the logic of that okay? Any queries about the argument? Okay, so now we've got another example. Maybe odds on, maybe we have a suspicion that the second one is going to be a positive example, since the first one was a negative example. It's not guaranteed, of course, but maybe we've got an inkling that that might be the case. So W2 is another subset of P3R. Again, it's defined in terms of a relationship on the coefficients. And this relationship says A0 plus A1 must be equal to A2 plus A3. First of all, we'll settle the non-empty. So clearly, W2 is non-empty, so let's just point to something which is in it. In A0 and A1 could be anything. E.g., the polynomial 2 plus 3x. You just have to arrange, just give the same coefficients to x squared and x cubed. So when you add A0 and A1, you get 2 plus 3 is 5, and it's clearly the same as adding A2 and A3. You get 5 as well. So it's certainly non-empty. You can certainly see there's an infinite number of polynomials in it. This is certainly looking more subspacey. It's looking more like a vector space. This kind of condition, I mean, it is a linear condition. You're just adding together stuff. And so, I mean, it certainly looks potentially good. W1 clearly contains the 0 vector, the 0 polynomial. The 0 polynomial has all 0 coefficients, so certainly the sum of the first two is the sum of the second two. So it's looking good. This looks linear, looks like a subspace. So we will prove it's closed. Prove it's closed under a linear combination. Okay, that's what the subspace theorem says you have to do. Okay, so this is quite different to giving a counterexample. Here, you want to keep things completely general. You're not talking about specific vectors or specific scalars. You want to keep it completely general. So you take a u and a v. So let u and v be any two elements of W2. Now, what's a good way of encoding this? And let alpha be any real number. Okay, alpha is a real number. But what's a good way of encoding the fact that u and v come from W2 into how we're going to represent it? Well, let's say that the polynomial u of x, we want to keep it general. So it could have any a0, could even have any a1, could even have any a2, but we can build in the condition that u is an element of the space W2 by our choice of how we're going to represent its final coefficient. Okay, because this equation a0 plus a1 equals a2 plus a3 is a single linear constraint on the four parameters. So basically, three of these parameters, any three of them could be chosen arbitrarily, and then there will always be a correct choice of the fourth one that will satisfy the condition. Okay, so as long as we make a3 equal to a0 plus a1 minus a2, you see this polynomial u is clearly in W2. And every polynomial that's in W2 has to look like this, doesn't it? Whatever for the first three coefficients it has, the fourth one must be equal to this combination of the other ones in order so that that condition is true. Now, you may have chosen to make the three arbitrary ones, say, the last three, and put in a certain combination of them for the first one. So you can do that in any way. So there's four different ways you could represent this, by making any one of the four coefficients equal to the combination of the other three. That seems the most natural way to represent it like this. So v of x, be another one of these. So I'll use these for its coefficients. So again, it can have any first three coefficients it likes, but then the fourth coefficient better be equal to this one. And we know it is because v is in the subset W2. Okay. Okay. Okay, so now we can do a proof of the closure condition. We consider alpha u plus v. Well, this is a polynomial. Well, it's alpha times a0 plus a1x, a2x squared plus I mean, it's debatable how much detail you need to include here. I mean, you could probably, I'd say as long as it's clearly explained, that accepts something that maybe just jumps to this final form. But what is this going to look like? Well, you just use the rules for scalar multiplication of polynomials and addition of polynomials. Scalar multiply polynomials by multiplying each coefficient by the scalar alpha. You add polynomials by adding together corresponding coefficients. So the constant coefficient of this one is going to be alpha a0 plus b0. The x coefficient is going to be alpha a1 plus b1. The x squared coefficient is going to be alpha a2 plus b2. And the x cubed coefficient, just to be a bit long, going to be alpha a0 plus a1 minus a2 plus the v coefficient, b0 plus b1 minus b2, this multiple of x cubed. Let's name these C1, C0, C1, C2, C3. Now the arithmetic is pretty trivial. You just need a good declaration and description from it here. From this, we see the condition C0 plus C1 equals C2 plus C3 is clearly satisfied. This is the membership condition for being in W2. Just check this. When you multiply this out here, and in other words, we're saying C3 has to be C0 plus C1 minus C2. That's the way we're phrasing it. That's the way we phrase the membership condition. And you can clearly see that it is here. This C3, this big long expression, is clearly gotten by adding C0 and C1. It gives you alpha A0 plus alpha A1 plus B0 plus B1, B0 plus B1. Then subtracting C2 minus this will give you the minus alpha A2 and the minus B2. So alpha U plus V is in W2. And the U and V were completely general elements of W2 that we introduced at the start. We built that condition into them by looking here, by specifying the fourth coefficient as combinations of the other ones. When you look at the linear combination, you see that again has to satisfy that condition. So W2 is a subspace by the subspace theorem. Is that okay? An alternative way to set this out might have been to, that's more or less the same. I mean, you might have stuck with A0, A1, A2, A3 up there, B0, B1, B2, B3, and then just to the side, write down the relationship that they have. A0 plus A1 equals A2 plus A3, and B0 plus B1 equals B2 plus B3. Then work out alpha U plus V, and just show that the required condition on the polynomial alpha U plus V comes from combining those two conditions on the coefficients of U and V. But it's more or less the same. I just chose to incorporate that relationship into the way I wrote down the coefficients of V. What you do need to be very clear on is the two types of response to such a question. Is this subset a subspace? It's either a general proof of the closure under linear combinations, which shows it is a subspace, or it's the pointing out of a specific counterexample, which is designed and constructed to show one instance where the closure condition is not satisfied. Okay. And that shows it isn't a subspace. Okay. So we'll proceed to 6 part B. 6 part B is a standard piece of bookwork from the course. So you've got a linear transformation between two general vector spaces, and you're being asked to prove that the image of T is a subspace. So like the things you'll be looking for here is again the use of the subspace theorem, and also clear, you probably better, the first thing you should write down really is the definition of what a linear transformation is, the defining condition for a linear transformation, and combining those two to show that the image is a subspace. So let's have a look at this, 6 part B. So the map TU to V is a linear transformation. This statement, what this means is that very similar to the subspace condition. So it's effectively talking about linear combinations as well. But it's not T being closed under linear combinations this time. It's the condition that T respects linear combinations. T does the vector space-like thing, does the linear type thing to linear combinations. So for every choice of scalar alpha and for every pair of vectors u1 and u2 from u, T of alpha u plus v must be equal to alpha T of u plus T of u. In English, you can remember this because this is saying the image of a linear combination is the same linear combination of the individual images. Okay? Very, very natural condition to have. Okay, and these are the well-behaved maps from well-behaved maps between vector spaces. And the image, we better get the definition of that as well. The image of T is the subset, and this is a subset of V, defined by, so this is the set of all T, T of little u, where little u comes from the domain space capital U. That's just a general image of any kind of map. Any kind of map from a domain to a codomain, the image of it is just the set of all the images, T of u, where you take every u from the domain. Okay? So this is your W, in the language of the subspace theorem, this is your W. Okay, that's the crucial thing to recognize. This is the candidate subspace, certainly a subset. This is certainly a subset of V, because all these elements, T of u, where do they live? Well, T of little u obviously lives in V. It's an image of the linear transformation. So it's certainly the right kind of thing. That might be a subspace, so it's a subset of V. So now we have to prove the condition from the subspace thing. First of all, we better show that T is non-empty. Sorry, the image is non-empty. How can I justify the fact that it's non-empty? I mean, it looks like a non-empty thing. It contains all these things for every little u from the vector space u. But like, if these are completely general, if we haven't been told anything about these subspaces, about these spaces u and v, what's the only kind of vector you can definitely point to that is undeniably in the space u? The zero vector. That's the only vector you can always name in any vector space. In any vector space, without knowing any detail about what kind of mathematical objects are in U or V, I can't point to anything else. So it is not empty as T of the zero vector, which happens to be the zero vector, but that's not important. T of U will be in the image. Sorry, T of the zero vector will be in the image of T. So it is a non-empty set. So now to prove the condition in the subspace theorem, so we will prove that the image is closed under linear combinations. So let vectors x and y be present in the image of T, and alpha be any scalar. We have to show that alpha x plus y, this is the conclusion we want to get to. We want to be able to show that alpha x plus y is also present in the image. Yep. That's the conclusion we're trying to get to. Now, in order to do that, we have to be able to say that T of something is equal to alpha x plus y. My number theory students will recognize what I'm doing here. If you're trying to prove something, go from a certain assumption to a certain conclusion, there's two ways you can get there. You can Well, you put down the assumptions, you put down the conclusion you're trying to get to, and you can either move the assumptions forward or drag the conclusion backward. How could you say that alpha x plus y is in the image? You have to show that it satisfies the membership criteria. To be in the image is to be T of something. And maybe we don't know what the something is yet. So our task here is to prove that there's a correct vector from U that goes in here, which gives you alpha x plus y. Which is clearly an element of the vector space T. Alpha and y are in the subset of V. But what does it mean to be in the image? To be in the image, it means there exists vectors u1 and u2 such that T of u1 is equal to the vector x, and T of u2 is equal to the vector y. Yeah, that's what it means to be in the image. And you got to make that connection. You got to get that condition down on the page. If you just keep working with a general looking x and a general looking y, the thing is, how are you going to distinguish them from all the other vectors in V? They're outside of the image of T. Okay. But this is the crucial thing that distinguishes vectors x and y. They come from something in U as a value of the map T. And then since T is a linear combination, and you see, I took the time to write down the definition of that above. This is crucial. So I just feed x and y into this here. T of alpha x plus y is equal to alpha t of x plus t of y. That's just the definition of a linear transformation. Yeah. This is a linear combination of two vectors, T of x. So, what did I do? No, I'm sorry, it's not x and y, it's u1 and u2. Mixed up my notation. These are the u1 and u2. Sorry about that. The x and y are the things living in the image. See, this is equal to alpha x plus y. T of u1 was x, T of u2 was y. So yeah, there is a vector that goes in this gap. It's alpha u1 plus u2. So the fact that there is a vector from U, and that this red vector is clearly something in the vector space U, is a linear combination of things from the vector space U. So that proves that alpha x plus y is in the image. Okay. So it's basically just interpreting the preservation of linear combinations condition for linear transformation, just kind of showing that that becomes the closure under linear combinations criteria for a subspace. So image of T is a subspace of V by the subspace. Okay, any queries there? Okay, part C then. Part C, unfortunately, there's a slight error in the way the question is phrased. of the error in the question. So it gives you a vector v, which is a polynomial from P3R. It gives you a basis of polynomials and asks you to find the coordinates of this vector v with respect to these three polynomials. The problem with this is in the word free. P3R is a four-dimensional vector space, so it can't have a basis consisting of just three polynomials. So this question needs a bit of fixing. It either needs the addition of a fourth polynomial to complete this basis, or, and this is what I suspect the issue is that this set of three polynomials will be linearly independent. So it is going to be a basis for a subspace of P3R. And I expect this polynomial, just because the way the question is set up and presented, I expect this polynomial will be present in the subspace spanned by these three polynomials. So it will still be, I expect it will still, might be possible to find the coordinates of v relative to these three polynomials, but this phrase can't say that that set is going to be a basis of P3R. So I would say this is a basis B of a subspace containing this polynomial v. That's what I expect is going to happen here. Well, I mean, this might be something that you do with transformation matrices, and that would have been the way I would have approached it if we had been starting from a basis of P3R, but the fact that we're not means it's a little bit difficult to put down what the transformation matrix would be, that the coordinate transformation matrix would be, because we don't know what a starting basis, we don't know any other kind of standard basis for the subspace. But we can still obtain the coefficients, I think, by just a little bit of stepping carefully in trial and error here. So let's do that. So v, which is equal to -2 plus 7x plus 3x squared plus 2x cubed. Okay, this is expected to be some a naught times the first polynomial, which is x plus x squared, plus some a1 times the second polynomial, which is 1 minus x, plus some a2 times the third polynomial, which is 1 plus x cubed. Now these a0, a1, and a2, these are not the original, sorry, when I should have used different letters, but at the top of the question, we specified a0, a1, and a2 as the generic coefficients of a polynomial. So here I'm using them for something slightly different, just the coefficients of this linear combination of these three vectors equal to v. I'm tempted to rename them just to make it nice. Yeah, I'm going to rename them just to not confuse them with the a0s earlier. So I'm just going to change them to v's. B0, B1, and B2. Now, are there any values that we can definitely pick out here? This is the thing, to step towards the values of B0, B1, and B2 by, well, maybe not trial and error, but just by a stepping process. Is there any particular value for one of them, B0, B1, or B2, that we can definitely declare now? Well, there's a couple of different routes into it. You see, for instance, only one of these three polynomials has an x cubed in it. Okay. So the only possible way you're going to achieve 2x cubed is if b2 is equal to 2. So you're not going to get any x cubes from those other places. Remember, the b's can just be real numbers. You can't introduce an x into the b's. So the only way you're going to get 2x cubed is if the b2 is 2. And moreover, the x squared only appears here. So the only way you're going to get 3x squared, there's no other x squared, is if b0 is equal to 3. So we're about to discover whether my correction to the question is correct. So by comparison of the coefficients of x cubed and x squared, we see that b0 has to be 3, b2 has to be 2. So our v is going to be 3 times x plus x squared. b1 we haven't said anything about for the moment. And b2 we've said has to be 2. Okay, then you just write this thing out so that we're writing constant on the left. So the constant is b1 plus 2. The x coefficient is 3 minus b1. The x squared coefficient is 3, as it should be. And the x cubed coefficient is 2, as it should be. So can we save this? Can we make this? Can we find a b1 that will turn this into v? So the b1 plus 2 has to be minus 2, so therefore the b1 has to be minus 4. Does that fit with the x coordinate? Yeah, it does. 3 minus minus 4, 3 plus 4 does indeed give you 7. So this implies that b1 is minus 4. So we can, so this shows that, so v is indeed in the subspace of P3R spanned by these 3 polynomials, x plus x squared, 1 minus x, and 1 plus x. As v is equal to 3 times the first one, minus 4 times the second one, plus 2 times the third. And it worked out nicely there, because the polynomials were structured in such a way that for a couple of the orders of x, that order of x was only present in one of the polynomials. So you were allowed, that enabled us to identify certain values of the coefficient, certain values of the coefficients immediately. The harder type of question would be where all 3 polynomials feature all 3 or all of the powers of x. You kind of just have to fall back on the default method of solving this kind of thing. Is to you would extract a system of equations for the 3 coefficients b0, b1, and b2. You get 3 linear equations for them, simultaneous equations for them, by comparing the coefficients, which you could then solve using Gaussian elimination. So that's the default fallback you can always fall back on. But oftentimes there's a quicker route through by just careful inspection. If that question had been, if you had genuinely been given a basis for the space, then you could have approached it using transformation matrices as well, which maybe I'll show you an example in one of the later classes today of applying that method as well, just to give a complete treatment to that.